Hey, and hi there. I started my lecturing and realized that my video was backwards. And what I was saying was A, how do? B, we finished our discussion of the basics of organic chemistry. You now know everything there is to know about organic chemistry, more or less. The main points there are we got carbon can form 4 bonds with something. We have 1 carbon is a methyl group, 2 carbon is ethyl, 3 carbon is propyl. Pretty much that covers a lot of our discussions there. Biochemistry, at least in terms of metabolism and things, is usually 6 carbons or less. So we then went through the functional groups, and I started writing them up on the board here, and when I realized and turned around and saw that my screen capture was backwards. But here they are. So yes, you do need to memorize whatever your functional groups. Have them written down on a piece of paper beside you when you take the test. I don't care, whatever. So the functional groups, we're going to be getting them into these and start fitting them into different kinds of food molecules. So you got to know. And we have alcohol, carbon with an OH group on it, an acid, a carbon with an OH group and a double bond oxygen, an amine group, which is a carbon with a nitrogen, and then a phosphate group. And I was just writing that one up when I turned around and saw that the screen was backwards. The phosphate group, and when I said phosphate, what did you say? I thought so. The phosphate group is PO4 with this great big negative charge. So we'll be picking up on how critical that is as we continue. So what we're going to do now is go through what a biochemist views as the major food groups, potentially, the major sort of macromolecules of living systems. And a couple of sort of vocabularies and ideas. What we're talking about is not just small molecules like oxygen and water. No, we're talking about really big molecules. So big that in the biz they're referred to as macromolecules. And this is pretty much a lot of what we eat and a lot of who we are is made up of these macromolecules. These are complex, very large molecules, really, really big. And they begin to actually change the consistency of the fluid they're in, and they can actually begin to carry out chemical reactions, all kinds of things. So, let's see. Well, the macromolecules themselves fall into these main classes. We have what are known as the carbohydrates, and these are sugars and sugar polymers. We've got the lipids, fats class of molecules, and we've got the protein class of molecules. Now, the 4th class of macromolecules that is presented in any biochemistry class or molecular and cell biology class is the nucleic acid class. And this is DNA and RNA, and in fact, I teach molecular genetics on Tuesday, Thursdays. It is the focus of the entire class, but for us, not so much. What we have here is your basic food groups. Now, there's the 4 food groups. I'm not sure what they are. The food pyramid, there's a variety of ways that the USDA has tried to develop sort of nutritional cartoons and things. So there are multiple food groups that the USDA might recognize. As a biochemist, there are these macromolecules. And nucleic acids are a critical macromolecule, but in terms of foodstuffs, we don't really worry about that so much. You don't sit down to a nice bowl of DNA. I mean, it'd be okay, but we don't do that. And your mom's never going to ask you, darling, are you getting enough DNA in your diet? No, we get plenty. So we're not going to talk about those guys right now. What we are going to talk about, though, are carbohydrates, lipids, and proteins. These are the things you're eating. I dare say, if you find yourself eating things that don't fit into one of these three categories, you really need to think about what you're eating. That is, don't eat glass, don't eat dirt, don't eat pieces of metal. Just don't do that. Carbohydrates, lipids, proteins. That's the stuff. Now, all of these guys have a lot of things in common and some very wonderful differences, and that's what we're going to get into. What we're going to do by the time we're kind of done with this discussion is we're going to be able to build a chart in which we can list carbohydrates, lipids, and proteins, talk about what they're made of, talk about some of the interesting features of them, and maybe some examples. That's what we're going to try to build at the end of this little discussion. We'll see how far we get. All right, so a couple of things to keep in mind as we start working through these different classes of macromolecules. Number one is these macromolecules are what we refer to as polymers. Good definition. And that is a polymer. It is a macromolecule, just a big-ass molecule made up of repeating subunits known as monomers. So made up of these repeating subunits, and they're called monomers. So a really good way to define these different macromolecules, carbohydrates, lipids, and proteins, is what are the monomers that make them up? And that's what we're going to be talking about. So polymers are around us everywhere. You know of polymers in plastics. And so there is a standard plastic called polyethylene. And it is a 2-carbon ethylene with a double bond in it probably. And it is linked together in this gigantic chain to make a sheet of plastic. High-density polypropylene. Propylene being the 3-carbon stretch, and poly meaning a whole bunch of them. And so polystyrene, polyvinyl chloride, that's PVC. Plastics are all polymers. But then biological molecules are also the macromolecules are made up of a lot of polymers too. And with a lot of these guys, we use both the macromolecule polymer and the monomer. But the monomers are always linked together to form these big polymers. And another thing to think about, when, as a general rule, when we're linking up these different monomers, if you're going to be saying, how do I link that guy up? The link is almost always through what's known as a condensation reaction. And we'll look at these in just a moment. Essentially, a condensation reaction is going to link together two monomers and generate a molecule of water. The way we break these guys down, the vocabulary term would be to break them down, is through what's known as a hydrolysis reaction. And hydrolysis is essentially adding a molecule of water across a bond, to break a bond. And so that's one of the ways bonds are being broken very often, is that the bond is being exposed, and then water molecules are getting in there and beating it up and breaking it apart. And so water is able to do a good job of allowing us to split apart all these different molecules. Now, the way we're going to go through this is take each macromolecule by itself, talk about its monomers, and then talk about the polymers, and then some interesting things about them. And then at the end, we'll be able to build this nice chart. And then you will digest that and spit it back out when I ask you, what are the macromolecules of food, and list their monomers and give me a definition or an interesting fact about them. You'll be able to do that. Great. Let's get started, shall we? Good. So we're going to start with probably my favorite macromolecule, the carbohydrates. Let's face it, it's sugars. And, I like my sugars, whatever. We'll see, though. There's actually some macromolecules that I really get off on. Just as a little point here, carbohydrates are what makes pudding thick. I love pudding. Don't make it nearly as much as I should. Another part of a lab we may do. We're going to try and do a kitchen thing. All right, so carbohydrates. Carbs. And you have heard about these. You've been told to avoid them, whatever. So carbohydrates. And a lot of these things, you got multiple names, and we're going to kind of go through some of the different names. Carbohydrates, the monomer is going to be a sugar. The sort of Latin-y term for this is a monosaccharide. And when we begin linking them together in a generic way, or a generic term, we produce something that's called a polysaccharide. So a polysaccharide is a bunch of sugars linked together. Now, there are a bunch of different sugar molecules, and the carbohydrate class can be actually very elaborate. We're going to talk about a few of them that are common in what we eat and what we see and manipulate. Things are common in food, but there's a bunch. All right, so the most common monomer for our carbohydrates, the most common monosaccharide, is the 6-carbon molecule known as glucose. Glucose, and here I'll draw you the structure in just a moment, for whatever it's worth. You don't need to memorize it or nothing. But glucose is a 6-carbon sugar. Now, in the sugar biz, we can have glucose, and you have consumed glucose if you've ever had Pixie Sticks. They're pretty much all glucose. Glucose is found in lots of different candies. It's all over the place. There is also another 6-carbon sugar known as fructose. It's a slightly different structure. And you find this, all kinds of things. High fructose corn syrup. Lots of fruits have fructose in them. Honey's got a lot of fructose in them. So these are different monosaccharides. Now, in terms of food, probably one of the more common sugars that you're familiar with is plain old white table sugar. That is, in fact, a disaccharide. And it's one of the things with this business of nomenclature. There's a bunch of different kinds of names for it. But plain table sugar is known as sucrose. And it is a link between glucose and a fructose molecule. So when you're thinking sugar, that's what you're thinking about, pretty much. Now, I've got a lot of glucose floating around, and we play around with sort of our lab-built Pixie Sticks. As it turns out, sucrose tastes quite sweet. Have a spoonful of sugar. Glucose isn't quite as sweet. If you've not had a Pixie Stick in a long time, you should go sample one. If you were to make a Pixie Stick out of sucrose, out of table sugar, it's actually a little bit too sweet. Glucose is not quite as sweet. And part of this has to do with how these different molecules interact in your tongue. You have spots in your tongue that bind to sugars and it says, ooh, that tastes sweet. And as we're getting into this, we'll talk a little bit about artificial sweeteners, which ain't got nothing to do with these molecules. Artificial sweeteners typically are chemicals that bind to the sweet receptors on your tongue and make you say, ooh, that tastes sweet. Don't be drinking artificial sweeteners. Not that they cause cancer, it's just because they are not good to eat. They don't taste good. They're not good for you. They don't do anything for you. And in fact, they are probably not serving as a way of reducing calories, but we'll talk about that in a bit. All right, so This is what glucose looks like. It's a 6-carbon sugar. And it's got 1, 2, 3, 4, 5, 6 carbons. There we go. So each carbon has a link to it. Beep, beep, beep. Now, this carbon, this little piggy, has a double bond oxygen. But every other one has an OH group on it. One of these alcohol guys. Now, if you recall, when we were talking about the notion of OHs, OHs have the ability to form hydrogen bonds. Remember, hydrogen bonds, my favorite bond. And what this means is that hydrogen is going to have a slight positive charge, oxygen will have a slight negative charge, because oxygen, being the electron hog, is keeping those electrons close to it. That means that sugars are able to form really complex mesh networks or mesh networks of hydrogen bonds. They can make this great big hydrogen bond cluster. And that is sugar's claim to fame, is the ability to form lots of hydrogen bonds. Now, sugars had the ability to swing around and link up with this oxygen and form what's known as a cyclized ring. And often that's how we see the structure. So you have this carbon with its OH sticking out, and then we've got a structure that looks like that, more or less. Don't worry about it so much, but we have the OH groups coming out. And this is the carbon with its OH out here as well. So there are a lot of different ways you can draw chemical structures. I kind of like drawing all the carbons out, but man, that was the way we were taught at Texas A&M. What do you want me to say? You also have the line drawing, and basically at each vertex it is assumed there's a carbon and whatever bonds it needs to be. If there's no other atoms shown there, like OH, it's just assumed to be hydrogens. So this zigzaggy lines, each zig is a carbon, and that's another way of drawing organic molecules. All right, so sugars can cyclize. Now, when we start linking together sugars, that's when things really get fun. And we've got 2 main sugar polymers made of glucose that we're going to be quite familiar with. When I tell you their names, you'll go, oh, I had that for breakfast. So the 2 primary sugar polymers, and it's actually an interesting kind of thing to think about. I'm going to try a different marker here. I really love my big black marker. I may get some different colors of those, but let's see how this works. We've got 2 different polysaccharides that are made up of glucose. So when you're looking around, eating stuff, looking at people, whatever, there's going to be 2. Can you see that? Yeah, not bad. All right. There's going to be 2 main polysaccharides and these are known as starch and wood, for lack of better terms. The more biochemically official term, starch is a molecule known as amylose, and wood is, of course, cellulose. Now, both of these guys are glucose polymers. And let's groove on this for just a moment. You may know that you can't digest wood. You can't digest cellulose. You can chew on sticks all you want. You can eat grass. But we don't have the ability to break apart cellulose. But cellulose is a great big chain of glucose molecules. Starch, on the other hand, This is the cornstarch, flour, potato starch. It's all starch. This is another glucose polymer, and we can break that guy down like a big dog. It has to do with the way the glucose monomers are linked together. When you look at the structures, unless you're really carefully looking, they look pretty much the same. One has a zig, one has a zag. And when we start talking about biochemical reactions, this is because the ability to break things down is very, very structural dependent. And we have the ability to break down the structure of glucose in amylose, but you ain't got the ability to break down the structural assembly of glucose molecules in cellulose. Now, ruminants like cows, they can break down cellulose, but it's because they have bacteria in their guts that are secreting an enzyme called cellulase that allows them to break it down. That's a pretty interesting thought. That so with starch, you may have done this 5th grade science experiment. In fact, go ahead, try it now. Get a saltine cracker or a piece of white Render bread, ball it up or crush it, throw it in your mouth, and sit there and drool on it for a while. Drool on it for a while. Maybe about 5 minutes or so. As you sit there and allow your saliva to act on this, your little cud, it'll begin to taste sweet. And what's happening is there is an enzyme in your saliva. We'll get into enzymes later, but it is a protein that can break down starch and convert it into just pure glucose, and you taste it as sweet. Now, the thing about starch is that you begin digesting starch in your mouth. And then when you swallow it, you get it into your stomach, you begin to further break it down, and you can break down starch into pure glucose really fast. And this is actually one of the things, kind of a fun twist here. We start talking about food molecules in terms of their biochemistry, and then in terms of the physiology, the way the body breaks them down, is that starch is starch. But there are some starches that are very finely powdered, a lot of surface area, like white flour or cornstarch. You can break those guys down really fast. And then there are starches that are held in large seed coats, or they're in like oats, and they're not nearly as easily accessible, and you got to kind of work on them in your stomach to break them apart, and so the starch is released much more slowly. Those guys are going to be sort of longer burning, and they don't actually contribute to your blood glucose as fast as real finely powdered, very easily accessible starches like in flour and cornstarch. And then, of course, we got just straight old sugar, but that's a different thing. So one of the things I think about is when you're faced with a diet choice, and you've got a donut on one hand and a bagel on the other hand, and you're saying, what should I have? Oh, I bet the bagel is the more nutritious choice. Nah. Bagel, donut, same thing. Both carbohydrate, and because they're made up of white flour, assuming it's a white flour bagel, not a whole wheat bagel, you're probably no more than 5 minutes difference in the amount of sugar you generate, except with the donut, it tastes sweet right away. The bagel is liberating its sugar in 5 minutes. Eat the darn donut. Don't go for the bagel. Have a donut. So, white flour. Now, I eat white flour all the time. I love baking with white flour. Nothing bakes as nice as white flour. White flour, poison. Stay away from it. I know. But whole grains, they're better because you absorb the sugars slower. All right, so that's our carbohydrate classes that we primarily think about. And we got starch and cellulose. Amylose and cellulose. So wood is a pretty tough material because we can't break it down very easily, but there are organisms that can. And just think about this. What if you could get the same amount of nutrition that you get from eating a bowl of pasta by eating a bowl of twigs? Just if you want to try that, I'll tell you, you can't. But now, another thing in terms of the food biz as part of the carbohydrate thing is this notion of what's called fiber. So fiber is indigestible carbohydrate. Back in the late 80s, early 90s, the fiber craze was everywhere. High fiber diets were quite the thing. And food companies actually began contracting with wood companies and with paper companies and getting wood pulp and putting it into food. So when you start looking at labels, there's fiber and then there's fiber. There's cheap fiber that is essentially wood pulp, straw, plant cell walls. Yeah, it doesn't count as carbohydrate because you can't break it apart. You can eat on it, and it's like, something to fill you up, but it ain't gonna do anything. But when we talk about, you need fiber in your diet, we're talking about something that would be referred to as soluble fiber. That's what makes oatmeal really gooey. And soluble fiber is much better for you than just wood pulp. So fiber isn't all the same. So there you go. Now, that kind of leads us to this point that this is what makes starches so wonderful for foods, because the ability they have to hydrogen bond makes them brilliant thickeners. So how many of you have ever made what is known as a bechamel? It is one of the French considered main bases of sauces. Or ever made cream gravy? All right. Ever made gravy? To make a bechamel, you take some butter, melt that up, maybe a tablespoon or two. You put in a tablespoon of flour. Put it in there and start stirring it. Now, what they always say to do is just stir it up and to kind of cook it a bit. If you're into Cajun food, you can really begin slowly cooking this and actually beginning to brown the flour, and that's what makes a roux. But for mac and cheese and white sauces, you just cook it around a little bit. And then you pour in, with this ratio, about 1.5 cups or so of milk. And you whisk it up really well. They say, you got to keep milk hot. Nah, just go in, dump it in, and start whisking. Now you have this on moderate heat, and as you're whisking it, it's not thick like a gravy should be, or a pudding if you want to make pudding. And you're going to be going, oh no, this isn't working, oh crap, something's not right. This is going to be really lousy gravy. But right around the time that it begins to show the first bloops of boils, you're going to see a dramatic change in the viscosity. All of a sudden, your whisk is leaving streaks, and you're going, hey, this is starting to look a little bit like a pudding or like a thicker gravy. And then when you cool it, it absolutely thickens. That is the main thing that carbohydrates can do, or particularly carbohydrate polymers. That's the thing they can do in terms of cooking, is they are thickeners. How? Glad you asked. Let's think about this. You gotta make the noise when you erase it, otherwise it doesn't erase. All right. So, in the plant and after the processing, we've got this starch molecule, glucose. Million glucoses. It is a gigantic freight train of glucose. Glucose, blah, 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 blah. Glucose, as far as the eye can see, literally, it is thousands to hundreds of thousands. I've never counted. I just made that number up. But regardless, it is thousands of glucose molecules linked together. A lot of glucoses. And when it is built and found in the plant, it's all kind of balled up. So just imagine like a wad of yarn all knotted together, all tangled up. And what happens is the hydrogen bonding that is occurring is within the molecule. We have hydrogen bonding between all those OH groups, forming what we would say is within or intra molecular hydrogen bonds. So these intra or within the molecule hydrogen bonds are keeping this ball of string balled up. Now, if you recall, we said hydrogen bonds are really weak bonds, and we can begin to break them with just a moderate amount of heat. And in fact, I will tell you, there is no hydrogen bond on the planet that can last or hold itself together at temperatures above boiling. Just doesn't happen. Hydrogen bonds always are going to break at 100 degrees C, 212F. So the hydrogen bonds in this ball, as you're heating it, they're beginning to break. But once you start to get to that boiling point, man, they are completely broken. So we add a bit of heat. Let's just go ahead and bring it to a gentle boil. And when we do, this ball of string, rather than being a tight ball, it opens up. And we got a long strand. And because we got multiple strands here, we've got this really smooth, slippery sauce that begins to change its viscosity, its thickness. But even more fun is as it cools, those hydrogen bonds reform, and we now have not within, but between. We have intermolecular hydrogen bonds. And now we've got this really big mesh going on, and this is going to thicken as it cools, and bada bing, you add a little sugar and you have got pudding. So as a general rule, anything that's not a wax, but any kind of stuff, goo, that is thin when you heat it and then thickens when you cool it, it is being thickened by hydrogen bonds. So if you were to think about this, adhesive tapes, they tend to lose their stickiness if they get hot. Like duct tape is great for this. It's because it's hydrogen bonded. And hydrogen bonding has this ability to form this fairly nice bond at lower temperatures. And so when you're making your gravy, it starts out very thin, and that's because you have simply balls of starch. They open up, and it definitely is a bit thicker now because those strands are really long rather than being little marbles. But as you cool it, it gets really thick. And so you've seen this with your gravies, is that at the stovetop, the gravy is thicker but not solid. You put it in the refrigerator, come back the next day for your leftovers, and it is going to be a definite semi-solid, a goo. And different starches have different characteristics, and so you can get a slightly grainier, crumblier starch matrix with flour. Cornstarch is a little bit different size, and it makes a smoother pudding-like thing. There's all kinds of different flours on the market that can be generated, have different chain lengths, and they're going to create different kinds of viscosities, but it's all the same principle. Yep, I love pudding. And Jell-O, which we're not going to be able to do the grand Jell-O experiment, I don't think, but I play with Jell-O a lot. Jell-O is a molecule that's got a lot of sugars in it. Also has a little bit of protein, which we'll get to. And it also forms hydrogen bonds. And one of the interesting things with Jell-O is if you ever play with Jell-O the way I do, if you put a package of Jell-O into cold water, you can stir it up. And if you stir it for a while, let it sit, the Jell-O will, in fact, suspend. It'll go into solution. And you can make sort of a sweet green fluid. But it's not particularly thick, and it won't gel. You got to heat that puppy up to open the hydrogen bonds and then allow it to cool. And it'll then gel. So you can get all these starches to go into solution, but unless you put a little bit of heat to them to open them up, they can't form these really big mesh networks when they cool to actually allow for pudding to be formed. All right. So that's what I had to say about our carbohydrates. And yeah, our next class is the lipid class. And for ease of uploading and for your dining and dancing pleasure, I'm going to pause here, erase the board, and we'll pick up on our next video on lipids. Isn't this whole thing so clever? Oh well. In the typical Monday night class, we'd say, okay, let's take a break here. It's been 35 minutes I've been talking. Good. I'm going to erase the board and I'll be right back. Bye-bye.